This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, and this is the last part, part 3, of our series on line edge roughness. We're at lecture 67. Last time we talked about roughness in terms of randomness, and the basic idea is that many things that we generally have considered in the past as being continuum variables, like intensity of light or concentration of the photoacid generator, are in fact stochastic quantities, and there's randomness associated with them. When we count the number of photons absorbed by a certain volume of resist, there's randomness involved. When we count the number of PAGs in a specific volume, there's randomness. There's randomness associated with the absorption. Every absorption of a photon is a random event with mean field values that we have come to know, like the Lambert law of absorption. But there's also uncertainty in the exact number of photons that are absorbed. The chemical events of acid generation. When we mix up a polymer, not every polymer has the same chain length. Not every polymer has the exact same number of blocking groups on that polymer. When we do reaction diffusion, there's randomness involved with every deblocking event. And then, of course, dissolution, a subject that we don't really quite have a good grasp of the impact of randomness on yet. We're still working on that. So all of these sources of randomness result in roughness on the edges of the features that we're trying to print. So the question is, what's the fundamental limits to how low we can drive this roughness? And what do we do to drive it? Well, one of the pieces of work that have informed my understanding of line edge roughness was this set of experimental data done at the University of Texas in collaboration with AMD, now Global Foundries. And they looked at making up lots of different photoresists with different amounts of quencher. So here's the quencher concentration, which went from no quencher up to a huge amount of quencher, 80%. And that resist didn't really work very well. But a lot of these resists worked quite well as photoresists, but with different amounts of base quencher, you could change the gradient in the protected polymer concentration, DMDX. And we saw before how base quencher steepens up the gradient, chemical gradients after post-exposure bake. And then they also changed these gradients by changing the image log slope, the nils, by allowing the image to go out of focus. So when you go out of focus, you get a lower slope of the energy gradient being put into the photoresist, which affected this protected polymer gradient as well. And then they measured the LER of the printed features, the standard deviation of the edge position. And all of these curves, with all these different base loadings and different amounts of defocus, fell in a fairly tight distribution of curve that follows a very specific trend. What is that trend? And is that universal behavior something fundamental about the way LER works? Well, I looked at this trend and fit a curve through it rather, which is this red line. And that red line fit a very, very simple equation. It's a 1 over x dependence plus an offset. So the standard deviation of the LER was some number, some constant divided by this gradient, which is the x-axis here, plus an offset. That is, it goes as a 1 over x dependence, but then it levels off at some fundamental value that you can't really go below. So empirically, we observe this behavior. And in fact, there's lots of other data that seems to show the same kind of behavior as well. But what is the cause of this specific form of how LER varies? Well, a very simple model, which other people have proposed as well, goes something like this. I'm developing away my photoresist and then just at the very end, just before the development is stopping at the line edge of my photoresist edge, there's some small error in development rate. Call that error delta R. Some small fluctuation caused by any of these things we just talked about. Numbers of photons, numbers of absorption events, etc. But the result is a fluctuation in the development rate. Well, how does that fluctuation in development rate translate into a deviation in the edge position? Well, a simple total differential says delta x is going to be the derivative dx dr times delta r. Well, if we think of delta r as a statistical variation in dissolution rate, then it will result in a statistical distribution of x positions. And that is nothing more than line edge roughness. So we replace delta x by sigma LER, the standard deviation of the x position. We replace delta r by sigma r, the standard deviation of the development rate. And then we see that LER is sigma r divided by this gradient in development rate, dr dx. Well, if we have a fairly high contrast development, and we assume that there's really no noise inherent in the development process itself, I'm not sure that that's true, but let's make that assumption, then this ratio of the standard deviation and the dissolution rate divided by the dissolution rate gradient will be about equal to the standard deviation in the protected polymer concentration divided by the protected polymer gradient. And that's in fact what we saw on this previous curve. All right? So this 33 numerical value from this curve fitting is in fact a sigma m, a standard deviation in a number of protected protected groups, the relative concentration rather of the protecting group. So we can see where this form comes from. Now, we could add some uncertainties inherent to the development process to this, but as I said, we don't quite understand them well enough to do that yet. So we'll just assume that those uncertainties are small, and as a result, the line edge position variation comes from variations in the number of protected polymers, protecting groups on the polymers divided by the gradient of the protecting group concentration. Then we simply add an extra piece to it, sigma naught. What is that? Well, it's simply the finite size of a resist molecule. That is, even if I had an infinite gradient, if I had a step function of deprotection, I would still see some randomness on the edge simply because of the random positions of the polymer. Sometimes the polymer is all the way outside of the region that's deprotected, and sometimes the polymer is all the way inside of the region that's deprotected, and sometimes a molecule is halfway in between. So there's some polymer size, something like what it might be, half the size of a polymer molecule, as the smallest noise level you could ever have on the edge of a photoresist feature. So we add that, and we have our final expression. What does this expression mean? Well, we're saying that the resulting uncertainty in the edge position is equal to a noise divided by a gradient plus a pixel size. This is like a noise to signal ratio. We often talk about the signal to noise ratio. This is just flipped upside. The noise divided by the gradient. The gradient is the signal. It's the information about where the edge is supposed to go. So noise divided by gradient is like a signal to noise ratio just upside down. And then we add onto it pixel size, the smallest that we can modify the edge position, which is the molecular size. And we have our expression. And this matches the experimental data, and it makes sense physically as well. So this will be the framework that we're going to use to understand line edge roughness. And we'll ask the question, what affects the three terms of this model? The noise, the gradient, and the pixel size. Well, the size of the molecules we use in the resist, the amount of acid diffusion, the dose, the quality of the aerial image we use to expose, etc. There's lots of things that could affect these, and with this simple framework we can understand what it would be. For example, the image nils. This is the gradient of the aerial image. The gradient of the protected polymer is directly proportional to that. So if we improve the image nils, we make the gradient higher and our LER goes down. Very, very straightforward. Let's look at some of these others and see what happens. First of all, we do have a model for the noise, sigma m. And we saw that last time. I won't go through it again, but it includes things like photon shot noise and PAG concentration shot noise and reaction diffusion and deblocking reaction. And it gives us a total uncertainty in the number of protecting groups. We also have models that tell us how all of these variables affect the gradient, dm dx. So combining those two things, we can understand how overall our LER might vary with these parameters. For example, polymer size. Suppose I increase the size of the polymer. What does that do to my LER? Well, first thing it's going to do is make sigma naught get bigger. Right? That is something proportional to the polymer size, so if I double the polymer size, sigma naught should double as well. But does it affect anything else, this polymer size? Well, yes, it does. It in fact affects sigma m. The noise in the concentration of the protecting groups. Why is that? Well, go back to this equation. This equation has inherent in it a certain volume. Right? What's the number of PAGs? The number of PAGs in a particular volume. What's the number of blocked groups? It's the number of blocked groups in that volume. The number of photons absorbed by that volume. Right? So it's got a volume built into the evaluation of this expression. So when I increase the volume that I average over, sigma m goes down. Because I have more protecting groups, I have more absorbed photons interacting, more acids interacting within that volume, etc. So what is the volume I should use to figure out the uncertainty within a volume? Well, it's the volume occupied by one polymer. The solubility of the polymer is a function of the total number of deprotecting events associated with that one polymer. And so I don't care about any one particular event. What I care about is the total number of events that happen within that polymer. So the events are averaged over the volume of one polymer. If I make the polymer bigger, I'm averaging over a larger number of events. And therefore I'm reducing the uncertainty of whether or not the polymer will become soluble. So larger polymer sizes, in fact, decrease the noise. But since they're increasing the pixel size, there's going to be an optimum. There'll be some polymer size that optimizes the LER. What is that polymer size? I don't know, but we've been trying to optimize our resists for a long time, and I'll bet empirically the resist companies have developed photoresists with polymer sizes that are pretty close to the optimum. That would be my guess. What about diffusion length? We looked at diffusion length last time, as a matter of fact. What does diffusion length do? Well, when you increase the amount of diffusion, you make the gradient of the protecting group go down. More diffusion means you smear out the gradients. You smear out the images that you're trying to print. So this is a bad thing. But diffusion also smooths some of the uncertainty in the number of protecting groups, because it's the catalyst, the acid, the catalyst of deprotection that's diffusing. When I make the diffusion length larger, I in fact make sigma m go down. What does that mean? There's an optimum. Right? We get smoothing caused by the diffusion of the catalyst. This diffusion also leads to correlation, which is an interesting topic we're not going to discuss. But it smears the way the image, and the result is an optimum diffusion length. I think the optimum diffusion length is smaller than the diffusion lengths we tend to use today, and so the trend in our industry is to try to push diffusion lengths to be smaller and smaller to get an optimum LER. What about dose? If we increase the exposure dose, we increase the number of photons. That increases the number of acids that are generated. That decreases the shot noise. So we'd expect the shot noise to cause this uncertainty to go down as I increase the dose. But interestingly, a topic we haven't really talked about, but if I increase the dose, I actually make the gradient go up to a point. To a point. There's in fact an optimum dose. Increasing the dose improves the gradient up to a point, and then it'll actually make it get worse, but this optimum is at a higher dose than we actually use today. So the result is, while increasing dose only makes things better to a point, we are today working at doses that are lower than the optimum, so increasing the exposure dose will always make our LER better, at least today. And certainly that's true for EUV, because we have so few EUV photons available to us. We're always trying to expose at minimum amounts of dose, and so higher doses are going to make LER better. So what have we learned about optimizing LER? There's an optimum polymer size. Current materials are probably close to that optimum. There's an optimum diffusion length. Current materials probably diffuse too much. And this optimum diffusion length scales with the feature size, so every time we shrink features, we're going to want to shrink our diffusion length as well. But there's a dose penalty for lower diffusion, as we've seen with chemically amplified resists. Higher amounts of diffusion causes more chemical amplification. It's a greater thermal dose. So if we decrease the diffusivity, we have to make that up by using a higher exposure dose to get the same number of deprotection events. And dose. There's an optimum dose as well, but the best dose is higher than the one we use today. And so our trend is to try to increase the dose if we can. Let's draw some conclusions about what we've learned about LER in the last 3 lectures. First of all, it is my opinion that LER is the ultimate limiter to resolution in any optical lithography scheme. It's in fact the ultimate limiter to resolution in e-beam lithography as well. But the limits become extremely obvious in EUV. EUV, unfortunately, is suffering from a light source that's not bright enough. EUV, remember, is extreme ultraviolet, 13.5 nanometer wavelength, and the first production tools are in manufacturing, being manufactured by the tool maker today, being shipped, and we're trying to see if we can get EUV ready for production in the next 2 years. But we don't have enough dose. And so we try to expose at very low exposure doses, and the result is very poor LER. Things like 4 nanometers of line edge roughness, 3 sigma, line width roughness to be more specific, about 4 nanometers of line width roughness. And if we're trying to print 20 nanometer features, well, that's 20% of the feature size. That's too big. We want to give line edge roughness maybe 10% of the feature size, maybe even 15%, but we're at 20%, and that's too much roughness, and we don't quite know exactly how it'll manifest itself in terms of the device, but it's not going to be good. We have learned a lot about LER in the last few years by studying it, but there's still a lot more to learn, and I think our models are good but not good enough. We can't predictively say this change in the process or the change in the material will result in this magnitude of decrease or increase in the LER. We also don't know exactly what the limits are. How low can we make the LER go? And because of that, what is the ultimate resolution limit? We need better understanding of LER. Otherwise, we'll just empirically find out what these limits are, and that may not be a pleasant thing. All right, so let's look at what we've learned so far in Lecture 67. As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material. What are the 3 terms of our basic LER model? How does polymer size affect those 3 terms? How does diffusion length affect those 3 terms? And finally, how does dose affect those three terms? There's other interesting variables to look at, things like quencher concentration, nils, as we've said, but these are the three variables that we explored in some detail. Well, that finishes up our lecture on line edge roughness. We have a few more topics to go on our quest to understand the limits of nanofabrication. Till then.